Okay, I'm going to do the problem that you're an astronaut on a mission to explore Earth-like planet. You know previously that the size and the planet are exactly like Earth, so we have ME, size and mass are exactly that of Earth. Planet has thick cloud cover, so you don't know anything about the rotation, but you land and you find that you feel much lighter, so much so that the acceleration of gravity seems to be only 1/2 of that of Earth. So assuming the true acceleration of gravity is equal to Earth, the effective acceleration is reduced by the centrifugal force. Okay, so we can just think about this as a vector addition, or we can think about like a free body diagram. But let's assume we are here on the planet. We land at the equator. So there is, let's just think about somebody not necessarily right on the ground right now, because then we think about the normal force, but anyway, we have like a FG0, let's say. That would be the normal mass times acceleration of gravity on Earth. And then we have a centripetal force, or centrifugal force, CF, that is due to how quickly the planet is spinning. Right? Actually, we're supposed to figure out the direction, but there is some rotation there, right? That's going to, in the accelerated frame of the planet, it feels like a centrifugal force. So we know just from this vector addition, right, I have my original gravitational force, I have the centrifugal force, and they're going to add to give me half. Okay, so maybe I need to make that a little smaller, but that's the basic addition. Okay, so FG0 minus the centrifugal force is 1/2 FG0. And this, what I mean is just mg0, where this is g of the Earth. Okay, just 9.8 meters per second squared. Okay, so our centrifugal force has the value, it's basically the opposite of the centripetal force, right? Which we know mv squared over r, v is omega r. So we plug that in, m omega squared r squared over r, m omega squared r. So the centrifugal force has the same magnitude as the centripetal force, but it's in the opposite direction. Okay, so we have m omega squared r, and here again we are at the surface of the planet, so that's really re. Okay, and then here, let's bring this over to that side. So we have minus that equals minus 1/2 mg Earth. Okay, so we want to solve for what omega is. We have a mass on each side that can cancel out. Okay, and our negative signs cancel out. So we get omega squared is acceleration of the Earth divided by the radius of the Earth. Take the square root of both sides. Okay, and then the question asks, what's the rotation period? So again, we got to use our relationship that the period is 2 pi over omega. So it's 2 pi re over ge. Okay, so if we plug in our values here, so we have 2 pi, radius of the Earth is, oh, did I forget a factor too? Yeah, I did. Okay. So 2 there. Okay, so then there's a 2 by the RE. 2, 6.371 times 10 to the 6 meters divided by the acceleration of gravity on Earth, 9.8 meters per second squared. Okay, so if we plug in those values, we get 7,164 seconds, or that the period is 1.99 hours. So that planet is spinning fast. Okay, and then part B says that, so we're traveling from the equator. We're going to send a drone due north, and we find that it actually ends up west of where it was supposed to. So then from that, what do we know about the rotation period? So remember, things at the equator are spinning with a larger linear speed. And so when they move up in latitude, they're going to be bending in the direction of rotation because they're moving faster than everything that's north of them, right? And, with the extreme case here, if you're standing there, you're just like spinning around in one spot. You don't have any linear speed. If you are standing on the equator, you're doing that whole circumference every time the planet rotates once. So, all right, so if things are getting deflected in the westerly direction, that means the rotation must be in that direction, right? So they're moving faster compared to, things that are moving slower and not moving at all in the direction of rotation. So then we have to use our right-hand rule. And if I put my fingers in the direction of rotation, right, this is the right-hand rule for velocity, fingers in the direction of rotation, my thumb shows the direction of the angular velocity. So that is our omega. I'll turn it the other way. Okay. Or we could say that if we're looking above the North Pole, the rotation is clockwise. So this is opposite of the Earth's rotation. Okay. If you wanted to also do that, this is in the direction of r dot cross omega. We could do that as well. It's a little trickier because r dot actually is into the page, because if we're going up in the sphere, our distance from the axis of rotation is getting smaller, but that change is actually into the page. So I think this is probably the easiest way to think about it, just in terms of things at the equator are going to be bending in the direction of rotation because they're moving faster.